our webinar, Design of a Control System Model in SimulationX using Calibration Optimization. My name is Stefan Matt, and today I'd like to show you how to perform a sensitivity analysis and an optimization of a SimulationX model using our software optiSLang. Before we start with the webinar, a short question. If you can hear me, please write a short text into the chat window. Okay, looks like it works. We can start with the webinar. At the beginning, some short notes. If you have questions, please enter them into the chat window. During the webinar, we will make short breaks and answer your questions. And a short hint about supported versions. From version 4.1, optiSLang supports SimulationX since version 3.5. Let's have a look at the organization of the webinar. After a first introduction in Metamodel, optiSLang, and our today's task, we go on with some details about process integration, sensitivity analysis, and optimization. And finally, some notes on further events to this topic. Okay, we start with the introduction. At first, some words about our company, Metamodel. Metamodel was founded in 2001, and now we have about 60 employees in our offices in Weimar and Vienna. We develop software, and our main product is optiSLang. And we also provide CAE consulting for mechanical engineering, automotive industries, and so on. In the field of virtual prototyping, the simulation with parametric models becomes more and more interesting. Real industrial models contain interdisciplinary processes. As a result, different servers have to be connected and performed in parallel. The resulting optimization problem may become noisy or ill-conditioned for a mathematical analysis. So we have extended requirements to the algorithms. The basic idea of optiSLang was to develop a software to handle exactly these industrial problems and requirements. With optiSLang, we offer an algorithmic toolbox for sensitivity analysis, optimization, robustness and reliability analysis, and finally, robust design optimization, also called RDO. optiSLang offers the beginner and the expert users an easy and reliable application with predefined workflows. Algorithmic Wizard helps to construct a graphical optiSLang workflow and to analyze your simulation model. All our algorithms have very robust default settings. That's why it is not necessary to be an expert for optimization and to know all the details about the algorithmic backgrounds. Our today's simple example is the design of a control system in simulationX. First part of the model is the dynamic system. The transfer function of the system should fit with a measured one from a real system. That is the first task of the webinar, and on the next page I will try to explain this a little bit more in detail. As a result of the transfer function of the dynamic system, the output signal differs from the input signal. Therefore, as a second task, the controller to compensate this deviation has to be designed. Step one is the calibration of the dynamic system. The picture on the right shows the given model in simulationX. To get the transfer function of the system, the input signal from the module input step is 1 for all times. Modifiable parameters of the system are the delay time, the system gain, and 2 time constants. The module output signal shows the transfer function of the dynamic system model using the currently chosen parameter values. This transfer function should fit with the measured one from the real system, which is shown on the left. That means task is to minimize the difference between the model output signal and the measured reference signal. As a first step, we need to connect the simulationX model with optiSLang. For process integration, we have to define the parameters we want to modify with optiSLang. This may be so-called design variables in the sensitivity and optimization part, or scattering variables in a robustness analysis. We not need to know what's going on inside the simulation model. For optiSLang, this is only a black box. After running the simulation model with modified parameters, we can extract several response values. So the first step of the process integration is to define modifiable design variables and response variables, which have to be extracted. After variable definition, we can add some properties. Design variables used for sensitivity analysis or optimization can have a continuous range between a lower and the upper bound, or discrete values with just certain steps. Also possible are string variables, for example, to switch between different models or materials. Scattering variables used for robustness analysis can have several types of distribution functions. And finally, response variables extracted from the model can be scalar values, vectors, or signal outputs, having an abscissa like a time axis or an ordinate, for example, a displacement or velocity. With optiSLang, we can connect every simulation software which has an ASCII text input and output file. For example, a model from the simulationX code export. We have some direct integrations like Endless Workbench, MATLAB, Excel, and simulationX, where optiSLang communicates via a CAM interface. Using our extraction toolkit, some further connections to read binary outputs like abacus or addends are also available. And in addition to use a single integration like at this picture simulationX, it is also possible to combine different models even with different solvers. At the example, is shown a simulation model as a combination of Python, MATLAB, Excel, and a text-based server. Today we will concentrate on a single simulationX model where we can use the direct integration. I think at this step we should switch to optiSLang and build up the integration workflow. Okay, after starting optiSLang, we have the possibilities to create a new project or to load an older project. After starting with the new project, we get an empty scenery to design a graphical workflow. First, we have to connect the simulationX model. Therefore, we use one of our helpful wizards, and the solver wizard helps to connect the simulationX model to optiSLang. We take the solver wizard and let it drop into the empty scenery. Here you can choose the required integration. For our example, we select simulationX. And afterwards, we choose the simulationX model. optiSLang starts the model inside simulationX in the background. And after loading, you get an overview with all available modules. Every parameter of each module can be used as a variable. Here you can choose the interesting parameters and register them as parameters in optiSLang by using drag and drops. If you have a lot of parameters, it is recommended to write an additional module in simulationX which provides all these parameters, like at this example, the module in out. Here we have all the interesting parameters. We select all the parameters, use drag and drop, and now the parameters are design variables for optiSLang. On the other hand, we can do the same with the calculated results. Make sure that the recording of the desired output signals is activated in simulationX. First, we add the output signal in results to the responses. So we can have a look at the model signal in the results and the final post-processing. As a second step, we add the same signal to the output slots. That is necessary to use the signal for a comparison with the measured reference signal. Now we use next. On this page, you can define the parameter properties and optimization properties. First, we have to define the ranges of the parameters. Both time constants are between 0.01 and 10. The system gain is between 0.1 and 5, and the downtime between 0 and 2. To the criteria tab, we come back later. And finally, a template of the system can be created, but our workflow is not finished because the comparison to the measured reference signal is missing. That's why we need currently no template of our system. Okay, now the integration of the simulationX model is finished. Oh, sorry, wrong page. The measured reference signal is given in a comma-separated value format file. In optiSLang, we can read this signal directly with a node. That means we switch back to optiSLang. We take the ETK node to extract the signal and let it drop on the connection. We take the output signal from simulationX and add it to the new slot of the ETK node. To read the reference signal, we use this node and we open the file with the reference. It's a text file. Okay, here we have all the values of the signal. In the advanced options, we have to define the semicolon as token separator. And now our reference signal starts in line 2. We have 2 columns and the full number of rows should be contained. Okay, now we can use the extract as signal option. Set the variable name to reference and add it to the internal variables. We switch to the internal variables tab. Here we have our reference signal. We need 2 additional internal variables. The first one is the signal of simulationX, and we get the signal from the input slot. Okay, using the instant visualization, we can have a look at both signals. And the last variable should be the difference between the signals, and therefore we use a predefined macro to calculate the Euclidean norm between both signals. That means between the reference signal and the signal of simulationX. As a result, we get only a scalar value. And the path to the reference file we have to define as absolute. Okay, now the macro calculates the sum of squared errors of every existing time point of the signals, and we use drag and drop to get to use all the variables as responses from our system. Okay, that's all. Now we can run, save our project, and we can see our project is running successful. Okay, for a later optimization, it is necessary to define an optimization goal. And in optiSLang, this is very easy. We open the system, go back to the criteria tab, and we define the value of the signal difference as minimization criterion using drag and drop. Okay, that's all to define the workflow. Now our final workflow is shown, the simulationX node with the loaded model system ISX and the ETK node to read the reference signal from the text file and to compute the signal difference. Our next step is to perform a sensitivity analysis. But before we start with this topic, a short question. Are there questions to the Prognosis integration part? If yes, please use the chat window. Okay, looks like there are no questions, and we can go on with the sensitivity analysis. The sensitivity analysis itself is a recount pre-investigation of the optimization procedure and may help to identify the most important parameters and to understand the model behavior. But before we go on with details about the sensitivity analysis, we build up the corresponding workflow in optiSLang. In this case, we use the sensitivity wizard, drag them onto the system head, and let it drop. Our parameters are already defined. Also our optimization goal. And now we have to select the sampling method and the number of samples. We use the standard settings. Okay, that's all. Now our system is morphed into a sensitivity analysis and we get 2 additional nodes. Okay, let's go on with the details. The sensitivity system scans the design space using a design of experiments. We prefer the Latin hypercube sampling with 100 simulation rounds. Main advantage of this method is a uniform distribution of all input parameters. All designs were evaluated at the simulationX model, and the responses were extracted by optiSLang. Afterwards, a meta-modeling approach named Metamodel of Optimal Prognosis, or MOP, is running, and here optiSLang identifies automatically the most important parameters and finds the best related metamodel with the relevant input and output variables. The MOP also quantifies the forecast quality of the metamodel and estimates a sensitivity measure in order to get an idea about which variables are necessary and which are not needed. Now let's have a look at the sensitivity results of our example. The MOP methodology was applied to the example of determining the characteristic values of the control system. And the obtained metamodel is a moving least squares approximation with a very good forecast quality of 97%. It illustrates that the signal difference is mainly influenced by the system gain and also a little bit by time constant 1. The second time constant and the downtime are minor important and were automatically filtered by the MOP. The metamodel also shows that only variants with a gain between 3 and 5 results with a small signal difference. Here the signal difference increases with decreasing system gain. The minimum signal difference will probably be in the range between 3 and 5 of system gain and bigger than 2 of the first time constant. Therefore, the design space for the subsequent optimization can be reduced to smaller bounds. Okay, our next topic is to perform an optimization with help of the additional information obtained by the sensitivity analysis. At this point again, are there questions? I go on. At the end of the webinar, we will have some time to ask questions again. The most important question is, which is a good and efficient optimizer for my optimization problem? In optiSLang, we provide three groups of optimization algorithms. If gradients can be calculated, gradient-based methods are very efficient. But often in numerical calculations, this is not the case, and their usage is not recounted. They cannot handle discrete parameters of failed designs. Failed designs means, for example, that optiSLang cannot extract an output value in case of a physically impossible condition or missing licenses. The second group are gradient-free optimizers like simplex or adaptive response surface method. They are much more stable as gradient-based, but limited by the number of parameters. They can handle discrete parameters and also some failed designs. If there are a lot of parameters and discrete values, then nature-inspired optimization algorithms like evolutionary algorithm or particle swarm optimization are suitable algorithms. They are very robust against noise and failed designs, but in contrast to the other groups, the result is often slightly inaccurate. Like you can see on this little overview, the choice of the right optimizer may be a challenge for the user. For this reason, optiSLang provides a decision tree and optimization wizard. With help of some information about, for example, number of parameters, type of parameters, or number of objectives, that means single or multi-objective optimization, optiSLang suggests the probably most stable and efficient optimizer for your optimization problem. Here you can use the suggested optimizer, and it's also possible to use another one. Okay, let's have a look at an optimization workflow of optiSLang. After using the optimization wizard with drag and drop onto the sensitivity system, we can give some more information about analysis status. If I have failed designs during the sensitivity analysis or solver noise, and optiSLang automatically detects the number of parameters and objectives and the type of parameters. In this case, optiSLang suggests the adaptive response surface method, and it's also possible to use another optimizer like simplex. Here we have some default settings. They are all very robust, so it's not necessary to change them. Okay, now we get an additional system. In this case, it's a simplex optimizer. The simplex is using the best design of the sensitivity analysis to start with the optimization and a final post-processing. That means this is our workflow. And now let's have a look at the results. The left picture shows the optimization history, starting with a signal difference of near to 1. The simplex algorithm calculates 160 variants to fulfill the convergence criteria. But after design 81, we have only a very small improvement. The right picture shows the extracted signal after calculated design, compared with the measured reference value in blue, and as you can see at the final value, the signal difference is very small. With the obtained parameter set of the simplex algorithm, the signal difference is with 0.2 very small, and the transfer function of the system fits very well with the measured reference signal, and so our system is calibrated. Okay, our second step, we want to use the determined system to design a suitable controller. Therefore, the optimal parameter set after calibration step was added to the system, and the controller parameters are the gain and the integration time. To have an influence to the output signal shape, 2 additional responses were extracted. The control time gives an information about the needed time to regulate the actual value of the output signal, finally into a given range of ±5% to the actual input value. And the overshoot describes the absolute difference between the input value and the output value. Optimization goal is to minimize the control time, having a maximum overshoot of 5%. The optiSLang workflow is almost equal to the previous calibration step. In this case, the ETK node to extract the reference signal is not needed, and here another simulationX model is integrated. During the sensitivity analysis, only 7 variants, that means the black points, fulfill the constraint conditions with a control time between 3.5 and 20 seconds. The MOP shows that the control time is mainly influenced by the system gain. And all successful designs have a controller gain smaller than 1. After sensitivity, a subsequent simplex algorithm is performed, and the upper bound of the parameter of the system gain is reduced to 1. The simplex needs only 61 simulation runs to reduce the control time to 2.55 seconds, with a maximum overshoot of 0.12%, which means the constraint is fulfilled. Now the second step to design an optimal controller for the calibrated system is finished. Okay, with this step we have finished our task for today. And now finally we have time for some questions. If you have questions, please use the chat window. Okay, if not, if you'd like to get more information about working with optiSLang, we offer some training programs for using optiSLang with simulationX. We have a one-day introduction seminar. Next date is April the 22nd at the ITI office in Dresden. And we have a 3-day introduction training about the whole spectrum of process integrations, sensitivity analysis, optimization, and calibration in Weimar. And also some one-day special trainings like parameter identification or robust design and reliability analysis. For further information about trainings and webinars, please visit our homepage. Okay, at the end, if you are interested in more information about optiSLang, doing case studies or pilot projects, do not hesitate to contact us. And finally, we have time to ask questions. Okay, if you have questions later, please contact our support hotline. I would like to say thank you for your attention. Have a nice day and goodbye.